So we've already seen two nice examples of using Feynman diagrams to reproduce a correlator. So what did we calculate? So first of all, we reproduced this two-point function using Feynman diagrams, and then we reproduced this correlator of just one, 5 to the naught. And we managed to get those terms correct. So now, as a last example of using Feynman diagrams, so let's say last example, what I want to consider phi to the 4, okay? So let's first of all calculate what the answer is, and then let's see if we can reproduce that using Feynman diagrams. So you know that this is given by taking 4 derivatives with respect to j of z of j, and then evaluating this at j is equal to 0. And you also know what z of j is. This is dj to the 4. Z of j is an infinite sum from n is equal to 0 to infinity. We've got minus g to the power of n. We've got n factorial. Then we've got 4 derivatives with respect to j raised to the power of n. And this is acting on e to the j squared over 2 alpha. And then we need to evaluate everything at j is equal to 0. And you have done many calculations of this type, so let me just write down the answer. So the first term, the term with n is equal to naught, is just 3 semifactorial over alpha squared. And the next term, the term at n is equal to 1, has got a g over alpha to the 4, and we've got 7 semifactorial. And we're going to drop all higher order terms, okay? By the way, you could easily calculate the terms of order g squared and make sure you get that correct. That's a good exercise. This is 3 over alpha squared minus g over alpha to the 4. Then what's 7 semifactorial? Oh, that's not my best, alpha to the 4. That's better. And then what is 7 semifactorial? Well, 7 times 5 is 35, times 3 is 105. And then there's order g squared. Good. So this now, it's this correlator that we're going to try to reproduce using Feynman rules. Okay, so let's see if we can reproduce that. Okay, so let's start off with order g to the naught. So what should we do? Because we're considering phi to the 4, we should draw 4 dots. So there are the 4 dots. And because we're considering order g to the naught, there are no vertices. So what do we have to do? We have to join these dots in pairs. So there's one possible diagram, but there's another diagram that looks like this. And then there's one more diagram where we join the first dot diagonally across. Okay, so that's the order g to the naught diagrams. Now let's see what these translate into. Now there is no combinatorial piece to this answer. There's no closed lines. There's no equivalent lines. They all collect to different dots. There's no equivalent diagrams. All of the diagrams look different. There are no equivalences. So nothing like that we have to worry about. There's no vertices. So for the first diagram, if we translate it, we just get 1 over alpha times 1 over alpha. So 1 over alpha squared. For the second diagram, 1 over alpha times 1 over alpha, 1 over alpha squared. And for the third, 1 over alpha times 1 over alpha. So we just get 3 over alpha squared. We could easily see that all 3 of these diagrams are going to give exactly the same answer. So we could just have written 1 over alpha squared and then multiplied by 3. Good. Okay. Sorry, that's a square. Good. Okay, so 3 over alpha squared, well, good. We got the first term in this correlator correct. Now let's take a look at order G. So what do we have? We have 4 dots still and 1 vertex. So what could we do? Well, the first thing that we could do is we could connect the vertex on its own. Let's sum over all possible ways of connecting these dots. So there's the second diagram, again with the vertex connected on its own. Then we've got a third diagram, again with the vertex connected on its own. And that's what it looks like. Okay, so that's one type of diagram we can have. Now there's another type that we can have. We might decide to connect this dot to the vertex and then through to the next dot. So we've got that. But we could also have decided to put this bubble on the other leg. Okay, so we could have done this. But then there's the diagrams of this type. We could trace that leg. And there's a diagram where we trace the bottom leg. But then there's a diagram where we trace the first leg going diagonally across. And finally, we might decide to trace the other leg going diagonally across. Okay, so 6 diagrams of that type. They all have basically the same structure. We've attached the vertex to one of the legs of just the order G to the naught diagrams. And of course, there's 6 ways to do that. And then finally, we have one more diagram that just looks like this. We just connect the 4 legs to the vertices. So in the first 3 diagrams, we've closed the vertex on itself. In the next 6 diagrams, we've closed 2 of the legs on themselves. And on the last diagram, well, the vertex connects to the 4 dots, so none of the legs are closed on itself. Good. So this is the complete set of diagrams. Try as you might, you can't think of something else. So let's now evaluate each of these and let's translate them into math. So we can take this, we can take this, and we've got that. So how many lines are there? 1, 2, 3, 4. 4 lines. So we'll have 1 over alpha to the 4. We've got one vertex, so we've got minus g times by 24. And now what are the factors? Now we do have factors. So we've got 1 over 2 squared. And this is because there are 2 closed lines. Those are for the 2 closed lines. And then we've also got a 1 over 2 because there are 2 equivalent lines. Okay, I'm doing this rather quickly, but I think that you know exactly which 2 lines are equivalent. Then there's only one diagram, so no bother about equivalent diagrams, and only one vertex, so no bother about equivalent vertices. So what does this give us? Well, we've got a minus g over alpha to the 4, and minus g over alpha to the 4, and then we've got 24 over 8. So this will be times by 3. Okay, good. So this collection of 3 diagrams, each diagram will give exactly the contribution that we had. So this sum of these diagrams is equal to 3 times 3 is minus 9g over alpha to the 4. So here's the first result for summing those 3 Feynman diagrams. Good. Now, let's look at this diagram. Like that, over there, and like that. So what is this equal to? Well, if we count the number of lines, 1, 2, 3, 4. So you've got 1 over alpha to the 4. There's one vertex, so we've got minus g times 24. And then when we come to look at the factors, we've got one closed line. So we've got 1/2. This is for a closed line. Then there's no equivalent lines. None of those lines have the same start and end points. There's just one vertex, so there can't be any equivalent vertices, and there's no equivalent diagrams. So what does this give us? Well, we've got minus 24 over 2 is 12. And then we've got g over alpha to the 4. Good. Now, every single one of the diagrams that is sitting here will give exactly the same contribution. So we can add all of these, okay? Good. So let's move this down here. There are 1, 2, 3, 4, 5, 6 of these. So this will be equal to 6 times the result that we just got, 6 times 12 is 72 g over alpha to the 4. Good. So that's the next result that we got. Excellent. And then finally, we have one last diagram. So there it is. It's this diagram over here. Let's translate this into math. So what is this equal to? Well, again, there's 4 lines. So we've got 1 over alpha to the 4. Again, there's one vertex, minus g times by 24. Then there's no closed lines. None of these lines are equivalent. They each connect to a different dot. There's no equivalent vertices. There's only one vertex. And there's no equivalent diagrams. So this is just minus 24 g over alpha to the 4. Good. And that is our third result. So now what happens if we sum these? Well, we've got minus 9 g over alpha to the 4 minus 72 g over alpha to the 4, and then minus 24 g over alpha to the 4. So what is this equal to? Well, 24 plus 72, so that's 82, 92, 96. 96 plus 9 is 105. So we get 105 times by g over alpha to the 4, and this is exactly the order g correction to the 4-point function. So we got that correct too. Good. So now I've given you a sampling of the use of Feynman rules. We reproduced 3 distinct correlators. We reproduced phi to the 0, phi squared, and phi to the 4. But you should know enough now that if you wanted, you could go ahead and calculate phi to the 6, phi to the 8, or anything like that. You should know enough now that you feel confident working with the Feynman rules, and you could calculate any correlation function you liked to any order that you like in perturbation theory. Great. So that's basically what I wanted to explain for this chapter. The only thing I want to do now is to discuss the exercises for this chapter, and we'll do that next.